Okay, so at least I have one happy face. I don't know. I don't know where the manners have gone in pandemic time, but they're definitely gone. Today is going to be slow, but I think slow is good after what happened last Tuesday. So just briefly, recap special orthogonal group in 2 dimensions and other rotations without reflections or inversions. And what I want to do today is something you know because it's called Fourier analysis. We want to determine irreducible representations of SO2 rotation group. Now we do have a representation that makes sense to us. If you remember, we had a representation that said, and this is just rotations in a plane. There's a 2x2 matrix that does that. It depends on one angle, one parameter, goes from 0 to 2 pi. And it's the usual cosine, phi, cosine, minus sine, sine. We can write it also as e to the minus I phi. Some matrix that today I'll call J. That's the way it usually shows up in physics. That's also 2x2 matrix. And this I and minus I, have been inserted twice so that this thing is a Hermitian operator. And the deal about it is that's a sensible rotations. That's how we think about 2 dimensions. But this is not actually an irreducible rotation. And why is that? When we look at this matrix, we have a rule that says sigma square, which is Pauli matrix square, is 1, which means that there is a Hamilton-Cayley equation here, which means that we actually can reduce this 2-dimensional space in 1-dimensional representations. And, it's the usual story. These guys, it's easy to figure it out. They have eigenvectors, 2-dimensional vectors, plus minus. Square root is to make them normal. And we either are plus and minus along the x direction, but these guys are actually complex. Nobody asked for complex, but that's the miracle of trying to find roots of polynomials. And with these eigenvectors, we have that our generator acting on the eigenvector plus minus gives me eigenvector back with the eigenvalue, which is very simple one. It's plus minus 1. So we have 2 1-dimensional spaces. This is the correct way to think about this representation, this particular 2-dimensional representation. It's reducible. After the diagonalization, this is what happens for the generator. And the general trick will be, we will have Hamilton-Cayley kind of equations. Once we have them, we can go to the group elements by exponentiating them. Diagonalized, this 2-dimensional representation actually becomes 2 1-dimensional representations. So you can think of them as e to the plus I theta, I phi, and e to the minus I phi, 0, 0. And these are 2 irreducible representations. From finite groups, we remember that there could be more representations. Remember how we got to SO2? We said, well, let's look at the pentagon and then hexagon and then entagon. And in the limit of n going to infinity, we got rotation in a plane from a cyclic group. That cyclic group was a billion, so the number of irreducible representation was n, and n is now going to infinity, so there should be infinitely many representations. So these are only two, but there should be many more. Let's figure out those guys. But now we're still at SO2. There is only one of these Hermitian matrices. SU2 will have three of them, three Pauli matrices. We're only using one to generate SO2 rotations. You might think, okay, so it turns out that when I think in terms of complex numbers, I have two complex phases as irreducible representations of rotations. It's cute, it's some mathematics, it's maybe convenient for something, but that's not what rotations in the planes are. It looks innocent now, and you're kind of used to Fourier series, just like you're used to Newton's laws, because you've been beaten with them, most of your adult life. But when we go to SU2, will actually be very surprising, because it'll say, don't think of rotations in three-dimensional space in terms of three real coordinates. You must think of it in terms of complex vectors, because that's the natural basis. That's really surprising. Then when we get to Minkowski, we'll learn in special relativity, it's a four-dimensional space-time with some metric in which there is a time directions and space directions, but it's real. All coordinates are real. But no, the group theory will say you will have to look at a complex representation, which is a four-dimensional complex vector, not the real ones. And that's the real thing. And you say, this is a mathematical nonsense. What do I care? But that's what electrons are, and positrons. Nature chooses the natural representation. So it's not some convenience for solving polynomial equations that you have to go into complex plane. It's really fundamental. And it's not because of quantum mechanics that we have to look at it. It's just fundamental in way we think about the spaces, even the ones like a three-dimensional space that we live in. So it's very surprising, this thing. But it's incomplete, because I just told you there have to be lots of, actually infinitely many representations. So let's get those.
Yeah, I was just wondering, the diagonalized matrix has the same phi, one is plus and the other is minus?
Yeah, it has phi multiplied by the eigenvalue.
Phi multiplied by the, okay, plus.
And, because it's 1 and minus 1, I'm not writing it out.
By saying infinite number of such irreps exist, are we saying any of those can be used to get J back?
No, this actually happens to be a faithful representation. Some representations are faithful, meaning they contain all the information about the system. Okay. And some are not. For example, there is a trivial representation 0, one by one matrix. That's a good representation. We use it all the time when you do our reductions to irreducible representations. But it doesn't tell you anything about rotations. It just assigns 1 to everything. But it's a representation. Now this one, phi minus phi, is all you need to know about rotations in a plane. The next ones that I'll find out, there'll be multiples of phi.
Okay.
And they're not 1-to-1, right? Because a multiple will go through 2 pi several times. It runs around the circle. Let's use letter U for unitary representation, because we know it'll have to be unitary, because we already know this from the compact groups, and this is limit of it. And the representation will have to satisfy multiplication rule for the group. which is here very easy because this is a billion group and angles just add up. And because addition is a billion, this is the same as saying phi 1. So that makes the problem quite easy. This will never happen again because we'll be looking only at non-abelian stuff from now on. We would like to have a list of possible irreducible representations. We will always start when we do continuous group. First, consider the generators of the group, infinitesimal steps that it makes. They close Lie algebra. Once you have figured out irreducible representations of that, then by exponentiation, you should be able to get irreducible representations of the full group. It's not quite as simple as that, but it's the essential thing. Well, I'll use Dirac's bra and cat notation, but it's just compact notation for vectors. Notation is, it was introduced in quantum mechanics, is often used in quantum mechanics, but it doesn't have to be that. Now we'll require generator that we now use letter J. We would like to find eigenvectors and eigenvalues of whatever is generating this representation U. And U is some matrix representation, unitary, but it could be any dimension. And J is the generator. So if you find that, then by exponentiation, we'll find that whenever we apply the finite rotation to such eigenstate, eigenvector, we will get e to the minus I phi alpha. U is e to the exponent of j multiplied by phi. But in this particular basis matrix phi takes values alpha. We notice now unitarity does something, because when we look at U evaluated any integer multiple, then by exponentiation, this will go up in here. But because we are running on a circle, remember, we are just finding representations of running around circle of periphery 2 pi. And after every integer run around, we should come back. So it must satisfy that, which means on this side that e to the I 2 pi m plus phi alpha should equal e to the minus I phi alpha. Phi now cancels out. We have e to the 2 pi m equals 1, which implies that m is any integer. So now we have learned something very important. So its geometrical meaning is what you need to know. What does this mean? We are running on a circle, so this field is oscillating, and eigenvectors have a property that we have an integer number of wiggles. You know from Fourier analysis, m is number of wiggles. And that will generalize, but not necessarily in trivial way, to all compact Lie groups, not abelian. So instead of oscillating on a circle, you might have a sphere or some other higher dimensional object that you find hard to visualize. So eigenmodes is something that has an integer number of wiggles on whatever the domain is in which is being explored by the parameters, continuous parameters transformations. So that's what that guy means. And now we can define eigenstates. and eigenspaces. So irreducible subspaces and irreducible representations which you label some way or other. For example, you put M here, not meaning exponent, but meaning just the representation labeled by integer M. And that's defined by saying that its generator acting on the eigenvector returns integer value M. And again, this notation, if you don't like it, you can, think of it as some eigenvector with components A1, A2. In this case, the reason why I'm pausing, because of course, this is an infinite dimensional vector in general. But whenever you have a truncated representation of the function, you are saying, I'm approximating a rotation in the plane by the, and Fourier modes. In practice, in numerical work at least. Lots of analytical work, you can take this off to infinity. So that's what, this notation says. It's really, in a limit, is really a function. And, we compute lots of those.
Dragging this back, but if we write M and then the vector M, is the first M representing the eigenvalue?
Yeah, so the first one is just a number. So this is a matrix. Okay. And this one operates on a space. And I showed this matrix explicitly on Tuesday. There was the big matrix with little blocks. I chose to show it in a real form rather than a complex form. But basically, in a correct way of thinking, it's a matrix that's infinite. It has 0 in the middle, and then it has e to the, it has,
IP 2,
1, 2, 3, 4, 5, and minus 1, 2, 3, 4, 5 along the diagonal in the limit of continuous group. So that's the matrix. This is just a number, an integer. And this is, what gives students who learn quantum mechanics for the first time, or engineers who learn partial differential equations and look at the linear solutions of them, function solutions of them. This is a function. And it depends in what coordinates you represent it. So when I drew this picture, I really meant there was a circle, a configuration coordinate, and then there was a function of the point on the circle, continuous parameter, like x, but called phi. So, these guys are functions. The basis functions are easy to understand. When you go to rotation, etc., it gets a little bit more complicated if you really want to write them explicitly, because then you have to learn about spherical wave functions, etc. So this is a long subject, and we usually do not need to explicitly construct these guys. Not in this course ever. There is a way of getting the predictions of the theory without explicitly constructing the eigenstates and eigenvectors. You just use the algebraic properties to get the answers. In other words, you work like we used to work with Hamilton-Cayley. We didn't actually have to construct anything. We just used these projection operators to get our results. Anyway, so that's what these equations are.
And so the e to the minus 2 pi m that we have written on the right top.
Yeah, so that was one of the representations.
Yes, I'm asking if there
So
was.
this, it turned out that this representation contained two irreducible representations out of infinity. It didn't contain the zero representation. It just contained rotate to the right or rotate to the left in a complex plane. In general, you have infinitely many representations, which they're called Fourier modes.
The m is an integer, and so the alpha, which is written on the top, is also an integer.
Yeah, we started with a real number because we didn't know. And when you start to study non-compact groups, like translation group on a line, infinite translation group, then alpha is any real number. It'll turn out to be what we call momentum in many applications. So x can be any value from minus to plus infinity. And its dual label of the irreducible representation, which is, what kind of waves you can put onto this.
And vary between minus pi to pi.
Well, alpha will be what we, people usually call either K or P for momentum.
Momentum, okay.
And that will be a real number. But for the compact groups, it takes integer values only. So the simplest example is U0. And that's a matrix where, alpha is just zero, so that's identity. And now you have seen U plus minus 1. I just flashed them again for you. So it's plus minus I m. Well, m equals 1, so phi. But then there is U plus minus 2. Two distinct representations. I'm saving space. And off to infinity. So this is really the correct way to think about rotations in a plane. The two things that we intuited by rotating a plane, they decompose in representation that we like is actually reducible into two irreducible ones. And the general irreducible representation for rotations on a circle is one of these guys. This is a little bit confusing here because I should really stick in the generator in a given representation, this J, but that one will be also labeled by plus minus 1, plus minus 2. And the only interesting thing that happens with it is that in general, we have a generator that has a form 0, minus 1. That's a convention, of course, plus 1, plus 2. And 0 is every place else in diagonal form. That's the general J for irreducible representations decomposed into sum over Jm is m in integers. So all this to tell you things you actually know, but this is what we transport to first non-trivial case, which is rotations in a plane. These things that are pretty obvious when we look at SO2 can be a little bit confusing for any other group. But if you understand the connection, the analogy between SO2 and SU2, for example, it'll be very helpful.